So we're going to start off talking about thermochemistry as our next topic here. And so, in chemistry we typically focus on properties and structure of matter. Chemistry is basically about matter, and it looks at the properties and structure and looks at the interactions between different types of matter, like you see in intermolecular forces, or we talk about chemical reactions. But there is another important aspect of chemistry, and that's the production and absorption of energy in chemical reactions. Chemical reactions supply living things with their energy they need to sustain life. So when you eat food, you're of course taking the chemical energy that's in that substance and then using that to keep your body alive. Chemical energy shows up with the reaction of fuels. When you talk about a car burning gasoline, is that it's extracting energy from a chemical reaction. The chemical reaction that happens in the engine when it burns the gasoline produces the energy that's needed to power your car. And in fact, the reaction of fuels make up about 80 to 90% of the world's energy. Most of the remainder tends to be things like nuclear energy and hydroelectric. A little bit's wind and solar, but 80 to 90% of the world's energy is by chemically reacting things like coal or natural gas or gasoline or things along those lines. Now, the study of energy and its transformations is called thermodynamics. And so anytime you're studying energy, how it changes form, that's thermodynamics. The study of the relationship between chemical reactions and energy, however, is thermochemistry. So that prefix thermo indicates, I normally think of thermo like temperature, like thermometer, but in this case is meaning more heat or energy. So that's what we're going to be studying here, is going to be thermochemistry. So let's recall our definition of energy. Energy is defined as the capacity or the ability to do work. Now, work is defined then as being the change in position, speed, state, or form of matter due to an applied force. So if you apply a force to something and it causes that object to move, then you've done work on it. If you take a ball and you squeeze it in so that the pressure increases on it, then that would be work that's done. And so anytime that you apply a force of some sort, and it may not even be an obvious force, but you apply a force to something and it results in the change in position, speed, state, or form of matter, then that's what work is. Now, energy, therefore, since it's defined as being the capacity to do work, energy we can say is the capacity to change matter. And energy comes in two forms, kinetic and potential. Kinetic energy is the energy due to motion. You throw a baseball, its motion as it moves through the air is kinetic energy. If that ball is spinning, then it also has kinetic energy due to its rotation. And so just energy in general that's in motion, that's doing work, is going to be kinetic energy. Now, the other type of energy is potential. Potential energy is fundamentally stored energy. It's always due to some relative position of particles that feel a force. So, for example, if that baseball is flying above the ground, then it has potential energy due to its height above the ground because its relative position to the ground, and it has a force on it, which is the force of gravity pulling it downward. So right now the important part, you don't have to go into detail on this, is just knowing that kinetic energy is energy due to motion, potential energy is stored energy. Now, in chemical reactions, we're interested in what's called chemical energy, and chemical energy is the potential energy that's stored in the bonds of the molecules. And so remember that chemical bonds are due to attractions between positive and negative charges, the protons and electrons in the atoms, whether it's covalent or whether it's ionic. And so because there is a force between those two, and those atoms are kept at some distance apart with the bonds, is that they contain potential energy, and that type of energy is chemical energy. Now, at the same time, atoms and molecules also possess thermal energy, and thermal energy has both a kinetic portion and a potential portion. The thermal kinetic energy, that part of thermal energy is due to motion, is the energy due to the vibration of the particles, the thermal vibration of the particles, which is basically their temperature. When you increase their temperature, the part of a substance, and the particles on average tend to be moving faster. And so as the temperature of an object increases, so does its thermal kinetic energy. And so therefore so does the thermal energy of the object here. The other type of thermal energy is called thermal potential, and so this is the energy due to the phase of the material. And so solids tend to have very low thermal potential energy, and then liquids have a little higher thermal potential energy, and gases would have the highest. And so as a substance transitions from solid to a liquid to a gas, thermal potential energy increases with each change. And so substances typically have both this chemical energy and this thermal energy at the same time. So let's suppose that we have two objects which have different thermal energies, specifically that have different temperatures, that we'll have a cold object and we'll have a warm object, and these two objects are going to be in contact with each other. And so whenever you have two objects with different temperatures and they're allowed to interact or they're in contact with each other, thermal energy will flow from the object with a higher temperature to the one with a lower temperature. So there'll be a flow of thermal energy from the hot to the cold. And the term that's used for this flow of energy is heat. And so heat is a transfer of thermal energy. So you wouldn't say that an object has heat. You would say that heat flows from an object or out of an object, that it's either absorbed by the object or that it is it's transmitted from or it flows out of an object. So heat will transfer always from the hotter object to the colder object until the point where the two objects reach the same temperature. So at some point, this heat will keep going over here until both these two objects are right at the same temperature. And so as we talked about previous sections, we have talked about heat before. We're going to use the variable Q for heat. And so sometimes we'll use a lowercase q as we're doing here. Sometimes we'll use that uppercase Q like we did earlier when we looked at heat and phase changes. They're both the same thing. In science, you'll sometimes see both Q's used, and so I wanted to use the little q here. So moving on. So energy in science, and this includes heat and other forms of energy, all sorts of kinetic and potential energies, are usually measured in one of two units. Either they're measured in calories or in joules, or they might be measured in some multiple of that, kilocalories or kilojoules or things like that. Now, in thermochemistry specifically, the most common unit of energy that's used is kilojoules. So kJ as our unit of energy. And so just to define some conversion factors here is that 1 calorie that we've used before is equal to 4.184 joules. And so this is the regular calorie, not the kilocalorie like a food calorie. And so 1 calorie is 4.184 joules. And then, of course, 1 kilojoule, since kilo is 1,000, will be simply 1,000 joules. So we can define the total energy within a substance, that is the total of all the kinetic energies, all the potential energies, as being that substance's internal energy. And so this is not an energy of like an object flying through the air. This is if we had this substance sitting on a table and we just said, well, let's just look at what energy is inside of this object entirely, we would call that object's internal energy. Now, internal energy ends up being really important in thermochemistry, but it's almost impossible to actually accurately measure it because it's not really doing anything that we can see normally. It's just the energy that's inside of the object. It's in the chemical bonds. It's in the thermal energy and in other forms. But it is not too difficult to find the change in internal energy, delta E. Recall that that delta symbol, the triangle, indicates change in. And so the change in energy is equal to the final energy minus the original energy, which is just our general definition of change. You take the energy of a system that it ends with, you subtract that from the energy that it started with, and that'll give you your change in energy. Now, for chemical reaction, ends up looking like this. The final energy is basically the energy of the products in the chemical reaction. The original energy is the energy of the reactants in the reaction, and so as a result, we can rewrite this definition of change in energy as being the delta E is equal to the energy of the products minus the energy of the reactants. So if you can figure out what energy the products have and you can figure out what energy the reactants have, you can take that difference and then that will give you delta E. And so you might say something like, if we were to do a graph with energy on this axis right here, that we might have, two things here. We have the energy of the products. Right here we have the energy of the reactants. And then if we wanted to find delta E, it's delta E is basically going to be the energy from the reactants to the products have gone up in this case, and so that is going to be delta E. The difference in those two is your delta E right there. So one of the key observations in science is the law of conservation of energy. And so we say conservation of energy, basically what we're saying here is that energy cannot be created and it cannot be destroyed. That the total amount of energy in the universe currently is the amount of energy that's always been here and always will. Now, that's talking about the universe as a whole, but it's also true within individual objects. But we have to look at something else there. We have to look at sort of how we define the object. Because we could talk about an object as being the whole universe, or we could say, I'm just going to look at, say, my computer or a particular chemical reaction, the reactants and products in that reaction. So if we define the matter involved in any chemical reaction as being a system, so S-Y-S-T-E-M, just like the normal word system that we have before here, so we'll say the system, and then let's define everything else in the universe as being the surroundings, just some terminology here. We'll note that there are two basic types of systems. There are closed systems, which are ones where no energy flows in or out of the system, and then there are systems that are open systems, where energy can flow in or out of the system. So if you have a closed system, then the energy in it is what's staying in it. No energy comes in, no energy goes out. If it's an open system, energy could go in, it could go out. Maybe it's going in and going out. But either way, energy can flow in or out of that system. In a closed system, since no energy flows in and out, and law of conservation of energy, energy can't be created or destroyed, the total energy is constant. That is, delta E is equal to 0. If it's a closed system, then the energy at the end, the final energy, is the same as the energy in the beginning, and so final minus original for energies is just going to be 0. Now, in an open system, however, energy can flow in or out of the system in one of two ways. Could be that the system loses energy by doing work on the surroundings, or gains energy by having work done on it. And so we call that the work is negative if the system is doing work on the surroundings. It is, let's say that we have some container that expands, now has gotten bigger, and so it's pushing outward on the outside. And so since it pushes outward, it does work on that other thing, and since it's doing work on that other thing, it's changing the matter outside of itself, is that it's losing that energy. And so we'd say that it's doing negative work here, or it's had negative work done on it. It does positive work on its surroundings. It loses that energy out to it. Other possibility is it could gain energy if, in the same way, is that the outside was doing work on it. And so basically something was pushing in on it, causing, let's say, the container to collapse that has the reaction going on here. And so in that case, work is being done on the chemical system, and so energy is flowing into it. And so those are two possibilities for work, is that it could lose energy if it's doing work on something else and the energy is flowing out as it puts the energy into the surroundings, or it could be the surroundings are doing work on the system, adding energy into the system, in which case the work is positive. Second possibility, if there's no work being done, or maybe there is work being done, but there also could be a case where the system could lose energy if heat were to flow out of that system. And so if heat flows out of the system, then obviously the system's going to lose energy. Other possibility, the system could gain energy if heat flows in to the system. And so for an open system, because of the fact that there are two possibilities for the way energy could flow in or out, we are going to say that delta E is equal to W plus Q. And so delta E is equal to work plus heat. So that if there is work flow into the system, that means the work is positive. If there's a heat flow into the system, that means Q is positive. If there is a work flow out of the system is doing work on its surroundings, then the work would be negative. And if the heat is flowing out of the system, then Q is negative. But either way, we can just find those amounts, add those up, and those will tell us what delta E is, what the change in internal energy is for our system. So let's look at a particular situation. So suppose that we have a reaction in a cylindrical container, and so we have some reaction that's going on inside this, from reactants to products right over here. And when this happens, there are two things that go on. First thing is that 50 kilojoules of heat, note the Q, are absorbed from the surroundings. So 50 joules of heat flow into the system, and at the same time, the result is that the system increases its volume. And so instead of being this size to start with, once that heat flows in, is now our chemical system expands out. So now it's that big. So it's been pushing up on its surroundings, and so it's doing work on its surroundings. And if it's doing work on its surroundings, it had to give energy away to those surroundings, and so we'd say it has negative 20 kilojoules of work done to it, because it's given away its energy, it's lost that. So the question is, what's the internal energy change? Well, remember that delta E is going to be basically equal to the work plus the heat. flow here. And so in this case, delta E is going to be equal to the work done on this. And so the first thing is it has done work on something else. It's given away its energy in the form of work. And so we would say negative 20 kilojoules of work, because it tells us that right here, that it's done. So it's lost that energy. Plus heat, it has gained 50 kilojoules of heat. And so we put 50 kilojoules right here. And so all we have to do is add this up. So delta E is going to be equal to negative 20 plus 50. And so that delta E is equal to 30 kilojoules. This system has gained 30 kilojoules of energy. We can sort of see this a little bit with another energy diagram like we have down here. We can see that, if we started off as a reactance, is the first thing that happened in terms of our energy is that it lost 20 kilojoules due to doing work on its surroundings. It gave that up to its surroundings. Then the heat flowed in, which is 50 kilojoules, and so that gives us an overall transition, a difference going from reactants to products of, we can see that 30 right there. So that would be an example of how you might calculate internal energy change. In a second case, similar type of situation, a reaction in a cylindrical container, this time absorbs 50 kilojoules of heat from its surroundings while being compressed as shown as left. And so energy is flowing into it, but at the same time we started off with a container that was this size, and then it squished downward until now the container is only this size right here. Now note that in this case, that because the container is being pushed in on, that that it's not true that the reaction is doing work on its surroundings. Instead, its surroundings are pushing on it. So the surroundings are doing work on the container. So that means in this case, the work is going to be positive 20 because that there's energy being added to the system by the surroundings. Now the heat is still going to be positive because there's a heat flow into it. And so if we wanted to find our delta E, as we just said before, it's going to be the Q plus, actually it's the work, never mind. So the work plus the heat, W plus Q. You could do it Q plus W, doesn't make a difference here. And so in this case, delta E is going to be equal to the work, which is positive 20, plus the heat, which is 50. And so that gives us a delta E of 70 kilojoules right here for the change in internal energy. Next situation, in this case, exactly the same as the last one. The surroundings are still compressing our system down here and doing work on the system, but this time the heat flow is out, and so heat is flowing out of our chemical system, and so because of that, Q is going to be negative because heat flows out. So in the same way we did before, still energy change is going to be the work plus the heat, and so the work in this case is positive 20. The heat in this case, though, is it's losing heat. It flows out of the system, so it's negative 50, and so our change in internal energy here is going to be negative 30 kilojoules. In this case, the container is expanding, and so instead of having work done on it, it is doing work on its surroundings. And so since the system is doing work on its surroundings, it's giving away its energy to that surroundings, and so the work is going to be negative. Q in this case is also negative because it says that the heat is flowing out of it. It's releasing 50 joules of heat, should be to its surroundings. Right there, mistyped that there. And so in this case, both the work and the Q are negative. So same as we did before is the change in energy. And internal energy is going to be equal to the work plus the heat. And so in this case right here, that's going to be equal to negative 20 plus negative 50. And so the change in internal energy is going to be simply negative 70 kilojoules. This time what we've done is we have put a cap on our container, and so because the container is sealed, the volume remains constant. So what we're going to have happen here is we're going to have a flow of heat out of the system, but how much work is done? Well, the substance is not expanding because the volume is staying the same, so it's not doing work on its surroundings. At the same time is that the surroundings are not doing work on the system because its volume isn't changing. And so because there's no expansion, no contraction, no work being done, work is equal to 0 kilojoules in this case. And so for this one, the internal energy change because delta E should just be equal to work plus heat right here. Delta E, the work we said, is going to be equal to 0, plus the heat is negative 50 kilojoules. And so then for this situation is that delta E is just equal to negative 50 kilojoules. Now, what's important to notice here is this circumstance of what happens if there is no work done on the system. If there is no change in volume, no change in pressure on the system, is that delta E is just equal to Q because of the fact that the work is 0. Only true whenever that work is 0, and that's going to be our next thing that we want to look at.